Right, let's start by looking at our data. So force, remember we calculated our force using weight. Okay, the weight equation, W equals mg, or weight is equal to mass times gravitational field strength. Okay, so remember our force was provided by weight. Okay, we were hanging weights off the spring, so force is weight in this case. Okay, each disc, each slotted mass had 100 grams of mass, or 0.1 kilograms. And remember, G on Earth is roughly 10, so we're just going to call it 10. Make it easy. So 0.1 times 10 is 1. So each slotted mass provided 1 Newton of force. We started our first reading, we started with no force at all. So the spring was completely, it just had nothing on it. Okay, so we just measured the length of the spring, worked out the extension. Remember, extension just refers to how much longer the spring has got. So if the spring started looking like this, okay, and we add a force to it, we add some force to it, so it stretches a little bit, okay, there we are. The extension, therefore, is simply the difference between its original length and its new length. Okay, so that's extension, which is x. Okay, I think it's actually referred to as E in the AQA revision guide. Okay, so E, extension. So that makes sense, therefore, then, that the first one, with no mass hanging from it, it's not going to have got any longer, so the extension is going to be 0. That makes sense, right? And then it got 2 centimeters longer when we added 1 Newton, and then a bit longer and a bit longer and a bit longer. But remember, the extension is always from the original one. Okay, so it's always from this original length. Okay, so it's always calculated from 0 newtons of force. So I've gone ahead and plotted a graph. Okay, force along the x-axis, extension up the y-axis. Now look at the shape of it. It's formed a nice straight line. Okay, it's a straight line, and it has gone, well, at least very close to the origin. So in a perfect world, it would have gone through the origin. We know, hopefully you know, that if your data forms a nice straight line like this, and it goes through the origin, then you can call it directly proportional. I can say that extension and force are directly proportional. So force, let's write this down, force is directly proportional directly proportional to extension. Yeah. This is what we call Hooke's law. This is what we call Hooke's law. Hooke's law, force is directly proportional to extension. Okay, Hooke's law. Hooke's law, force is directly proportional to extension. How do we know it's directly proportional? Well, the graph, the data, forms a straight line, it goes through the origin. How else do we know it's directly proportional? Well, directly proportional also means if you double this axis, then you will also double this axis. If I double the force, I will also double the extension. Well, let's have a look. Let's take, say 5. Okay, 5 gave us an extension of 16. Double this to 10. Maybe 5 is a bad example because we didn't actually get to 10 newtons. Let's do 3 instead. So 3 gives us 9 centimeters of extension. Double that to 6, and you get 19, which is pretty much double. Okay, pretty much double. In a perfect world, it would be double. Yeah, and that's what Hooke's law is. Force is directly proportional to extension. It's directly proportional. If you double this axis, if you double the force axis, you double the extension axis. It forms a straight line. It goes through the origin. That's Hooke's law. Now, if we were to continue adding masses to it, okay, it will continue getting longer. The spring will continue extending. what will actually happen eventually is it will hit its limit of proportionality. At some point, it will stop being proportional. Okay, this will stop being directly proportional. In other words, the graph will no longer form a straight line. Suddenly, it will start getting easier and easier to extend, where less force required to make it get longer, and it will eventually it will reach its limit of proportionality. Its elastic limit as well, when it will permanently deformed. At this point here, it becomes permanently deformed. It means you can't actually, it won't actually return to its original length. If I pulled it so hard, then the spring will stay extended. Yeah, that makes sense. You've probably seen it happen before. Maybe you've dismantled your pen, got the spring out of the pen, and you've pulled it, and it's extended permanently. You've just extended your pen spring to beyond its elastic limit. It's now permanently deformed. Right, what else can we say? So, if something is directly proportional, we know that force is, so you might have seen the symbol in maths, force is directly proportional to extension. We can replace this alpha directly proportional symbol with an equals, and then put a k in there for a constant. F equals ke. You may have come across this in the revision guide already. Force is equal to k times E, where k is the spring constant. Okay. E, we've already discussed, is extension. And then F, of course, that's force. Okay. So spring constant times extension. Spring constant basically just refers to how stretchy a spring is. Yeah. The higher the spring constant, the stiffer the spring is. So if you've got a really weak, the springs that I was using in it would have had a low spring constant compared to a suspension spring on a car, which is much stiffer. Okay. So spring constant, more stiff spring. Okay. Okay.